Thank you very much. Thank you for the opportunity to give a little introduction about Delo Industrial Adhesives. My name is Markus Willemeit, and I'll be taking you into the world of light-curing adhesives now. Let me start off by giving a few slides about Delo as a company. What you can see here is the headquarters in Windach, that is in Germany, southwest of Munich. And I'll just give you a few numbers about Delo so you get an idea what we are all about. We're a family-owned company with revenues of 175 million euros annually. Currently, we have 860 employees, and we are still growing quite rapidly. To give you an idea how and where you have already come into contact with Delo Adhesives, maybe without knowing it, I'd like to take you on a very short tour. Maybe you got to work today in a car, and there you had the first interaction with Delo Adhesives. There are automotive camera modules. There's display integration where the displays are bonded into the frames, and various sensors like temperature sensors and ultrasonic sensors. And in electric motors, which become more and more important as e-mobility is on a rise, there's also Delo adhesive in it. And chances are you already had your mobile in your hand, and there as well are different bonding tasks hidden inside of mini loudspeakers, inside of compact camera modules, and in various sensors or micro electromechanical systems like a microphone. So just to give you a hint, I've been talking about bonding tasks, so adhesives, but there are two other things that are very important for Delo that are the dispensing and the curing equipment that my colleague Michael is going to tell you later on, and of course our expertise and our technical consulting. Where is Delo? We're an international active company. Our headquarters is in Germany. There are subsidiaries in Shanghai and in Boston, both with their own lab facilities, and as well as in Japan and in Southeast Asia, in Singapore, and on the west coast of the US. So just a very brief introduction of Delo as a company, and I will jump right into light cure. I'll be talking about light curing adhesives. My colleague Michael is going to show you and introduce you to LED lamps and their technology. And I'll be showing you some applications where those adhesives are being used. But before we go into that, let's start with a question: what is light curing? So what's the process like? And we'll start with the basics. The task is usually to bond two things together. And for light curing, that means you have a component in black here, you dispense the adhesive on top of it. You have a second component, note that that is transparent, so the light can pass through it. These are the two joined parts with the adhesive between them. And finally, the curing step, where the light leads to curing or hardening of the adhesive. And as you already noted, one component needs to be transparent for the light to reach the adhesive, but there is a process, a neat little way to get around that we'll see later on. There is an option for joining two opaque components. Very well, that's what light curing is, but why do we use it? So let's look at some advantages of light curing. There are three main aspects here, and one very important one is that it's very fast. Light curing adhesives cure very fast and therefore allow very short cycle times, and they generate therefore high output, high UPH, while still maintaining a very high reproducibility in those. And this is especially used in components for mobile phones, for example, where you have a lot of them being in production. Another point is easy handling as those adhesives are one component, and so there's no mixing necessary. That's kind of an advantage everywhere. And the last one is maybe one of the most important ones, and that is those adhesives are curing on demand. They only cure when you want them to, when you switch on the LED lamp, when you irradiate them by the push of a button. And that means no long processing, very long processing time, sorry. You do not need to fixate the components after you irradiate. And those adhesives allow for very precise positioning of the parts. And that's, for example, very important in a component like this, an automotive camera module, where it's important to align the lens or the lens components here to the housing that contains the chip, because that's very important for the optical quality of the camera. So you can see those advantages are applicable in a wide range of industries. Okay, this was the why. Let's dive a little deeper into on, let's say, a molecular level. Let's look at the basics of light curing, of how it works. And we're talking about how we get from a liquid adhesive to the solid high-tech plastic such an adhesive becomes when it's cured. So when we look into the cartridge, there are single building blocks that are all from the same type of monomer. And if we activate that, if we cure that adhesive, what happens is that those monomers are going to form long polymers. They're going to form long chains. And this is a very simple picture because it's spaghetti-like. In reality, those are going to branch out and form a 3D network that's going to give the adhesive its properties in the cured state. And as we're talking about light curing, how do we get from monomers to polymer? We're using light to activate and to start that reaction, this polymerization. Okay, this is what happens when you irradiate the adhesive. Now, there are two aspects that are important for, are very important for light curing. And one thing is, it's kind of a two-part thing. It's the adhesive that receives the light, that absorbs it. And on the right, you can see here the absorption spectrum of an adhesive, meaning what wavelength, what color of light can the adhesive use in order to get cured. And on the other end, the sending end, is the LED lamp that gives off light. And unlike the sun, it's not going to, those lamps do not give off every wavelength, but a specific part of it. In this example, it's a lamp that has its peak at 400 nanometers. And now in order for the adhesive to cure, it's important that those two spectra match, that the adhesive can actually use the light the LED gives off. And that is the case in this little example here. So the wavelength of lamp and adhesive do need to match. Okay. That was the first aspect. Going to the second aspect, I'd like to take a little detour and show you an application example to illustrate that. So what you can see here is a smartwatch and some of the components you can find in it. There are mini loudspeakers, compact camera modules, but we're going to focus here on the sensor that may sense the pulse or the oxygen level in the blood. And this sensor is protected by a cover glass on top here. And we're going to do a little cross-section through that housing to make things a little clearer. So that's the housing of the sensor. The sensor is down there. Above that, we would dispense adhesive in order to bond the cover glass material on top of it. Now, if that's a light curing adhesive, we would need a lamp to cure the adhesive. But note that the light needs to penetrate the cover glass material in order to reach and cure the adhesive. And therefore, the transmission spectrum of this material up here, the cover glass material, becomes important. When we look at the graph here on the right, you can see that here's the wavelength, and on the y-axis is the transmission rate. So the higher the transmission rate, the more light will pass through a specific material. Let's do an example. Let's say we're using a lamp that has a wavelength of 365 nanometers, about here. If this cover glass material were actual glass, float glass, up here, everything would be fine. We have a transmission rate of 80%, and that means 80% of the light of the lamp is going to reach the adhesive. The adhesive is going to cure, and it's going to do it quite rapidly. But if we were to use PMMA as a cover glass material, things would look quite differently. Now the transmission rate is pretty near zero, and nearly none of the light is going to reach the adhesive, which means very long unusable curing times or no curing at all. So the second aspect here is that the transmission of the substrate you use is very important here because it affects curing time and curing degree. Very well. And now with this, I'm going to hand over to my colleague Michael, who's going to show you, grant you a deeper look into the LED lamps.
Thank you, Marcus, for the introduction and the basics of light curing adhesives. Now I want to talk with you about LED lamps that are used to cure light curing adhesives. UV or light curing technology has a quite long history at Delo. In 1990, we produced our first discharge lamp that you can see here, the Delolux 01. And over the years, new models were created based on technological improvements and changing market demands. Till the last discharge lamp, the Delolux 03S, was discontinued in the year of 2016, which also marks the end of discharge lamp heads in our product portfolio. And that's the reason for that is that in 2007, we decided that we want to move away from the discharge technology and focus our lamp technology on the LED type of curing lamps. And in 2018, we created our first LED curing lamp, the so-called Delolux 80. And since then, our lamp head portfolio with LED lamps continuously has grown over time. So we created different shapes of lamp heads and also different cooling mechanisms, always focused on the market demand. But what's the main difference between discharge lamp technology and the LED lamp technology? To give you a brief overview of the difference between the technologies, here you can see the old Delolux 04, which was a discharge lamp in our portfolio. It consisted of a base unit that you can see here, this block, and the light guide. Inside of the base unit, there was a discharge lamp bulb, and this discharge lamp bulb was used to create the light or to get the light created. And for that, so to start the light process, the discharge lamp needed to heat up first. So you start the base unit, and then it takes some time for the discharge lamp bulb to get to its full heat and its full power output. And that is quite of the interesting thing about discharge lamp heads. You always have them on in your process. You can't just start and stop your lamp base unit, because then otherwise you always have to wait for your lamp head to start up again or to heat up again. So to overcome this problem, as to say, you can use a mechanical shutter here in front of the lamp head, so you can start and stop the irradiation by just putting some mechanical blockage between the lamp head and the part you want to cure. But nevertheless, the light is always on, so to say. And as you can see here, service life of one discharge light bulb is quite limited with 1,500 hours of service time. And that was a reason for us, one of the many reasons why we changed to the LED technology. And the LED, the working principle is we have an LED die with a semiconductor interface between a P and N doped range. And as soon as voltage is applied, this semiconducting range generates light. And as long as we have a voltage here, light gets generated. With the voltage, turning voltage on and off, we can easily start and stop the irradiation process with an LED lamp head. And that has also the benefit that we don't have to always have the lamp on. And this also increases the lifetime. So with an always running LED, we get a lifetime of more than 2,000 hours. Another interesting fact is we can adjust the intensity here on an LED lamp, while with the discharge lamp, we can just turn it on or off. The benefit of the discharge lamp on the other side is that it puts out light with all wavelengths that are possibly to cure an adhesive, while, as Marcus said, with an LED lamp, we have a peak wavelength in a specific range, like 365 nanometer, 400 nanometer, or 460 nanometer. So you always have to check which adhesive you are using and which light wavelength range it needs to get cured. So now I want to show you some application examples where our lamp heads can be used, and also the reason why we have different lamp head designs, like different geometries and different angles of irradiation. Here you can see the Delo 503. And the special thing about the lamp head, it has a 30-degree angle, which enables us to be very space serving in a process where you have limited space in the C direction. Another example with the Delo 504 here, also we need in this application high intensities to cure the adhesive in a very short time, but we are quite limited with the space we can occupy in the machine here. If space is not such a problem because we have large parts, we also have area lamp heads, or you can use area lamp heads to cover more space with light of high intensity. In that case, you just have to look at how homogeneous the irradiation really is in your application. And if you have, for example, in this case, a quite high distance between your part top and your adhesives that is located inside here, you can use also lenses on our, for example, Delo 505. Talking about intensity and homogeneity, here you can see some intensity profiles for our Delo 50 X1 and our Delo 20. What you can see here is that in different colors, we have different working distances and the resulting intensity profiles at these working distances displayed. With working distance, I mean the distance between the lamp exit and the substrate or the adhesive you want to cure. What you can see here is quite a good takeaway. With a very short distance between lamp head and substrate, we get the highest intensities, also with the area lamp heads, but we are quite limited in space. Like here, you see we only cover like 1 mm in diameter with the high intensity, and on the flanks, we lose quite fast the intensity if we go outside of this sweet spot where we have the high intensity. So what's to take away from here? Depending on your intensity need for spot lamps and area lamps, you also have to check which intensity profile does your lamp provide and which distance you therefore need to cure all the adhesive in your target area. An interesting thing you can do here, if you want to cover larger areas with high intensity, you can combine area lamp heads, for example, in this case, the Delo 20, to cover a higher ground. The purple disc here should resemble an 8-inch wafer. And here in the yellowish part, we use also a reflective funnel, and with a combination of more lamp heads, even with some distance and some distance to the substrate and some reflective funnel around the lamp heads, we can achieve high intensities and high homogeneity in the target area. So to sum it up, your advantages with Delo-Lux lamps and LED lamps in general, you have a low heat input into the irradiated components because it's a cold light, so to say. You don't have a discharge lamp head that gets, well, quite hot. And you have very long service life of more than 20,000 hours. You have low maintenance costs. The power of the LED can be adjusted to fit your process, and you have the full lamp power directly after startup. You don't have a heat up phase like with a discharge lamp. And for example, as I mentioned, you don't need a shutter if you don't want to cure all the time, or you can't cure all the time because you have moving parts on a tray, for example. The LED lamp can just be turned off. The disadvantages, of course, we also have to highlight that. We have some higher investment costs compared to a discharge lamp, and we don't have like a wide range of wavelength, but we have quite a focused wavelength for an LED lamp. As mentioned, 365, 400, and 460 are the most common wavelengths for LED lamp heads. So that would be my part, and Marcus will continue from here to talk with you about acrylic and epoxy adhesives.
Okay, thank you, Michael. And now that we're talked about the LED lamps, let's talk about the light curing adhesives themselves. I'm going to introduce you two types of light curing adhesive. That's going to be light curing acrylates and light curing epoxies. So we'll start with the acrylates. Some basic properties here. Curing is possible in 1 second, in some cases even below that. From a mechanical standpoint, elongation and tear they are rather flexible, so 4% up to 550%. Acrylates are typically on the upper end of that range. So this is something, these are adhesives or sample specimens that show such a large elongation and tear. And those adhesives are transparent, which definitely makes sense as light needs to pass through them for them to cure. There are also limits, of course, because as noted before, one of the components needs to be transparent, and the layer thickness of the adhesive itself is limited to around 5 millimeters, which is typically not a big problem because most bonding gaps layer thicknesses are way below 1 millimeter. And there's no light curing possible in shadowed areas. You do need to irradiate the whole volume of the adhesive. Now, if we look down here on the bottom right, we can see this little graph that shows time on the x-axis and the curing degree on the y-axis. So 100% curing degree means the adhesive is fully cured and is not going to change in its properties anymore. You do need to switch on, or the light has been switched on, the lamp has been switched on here at time 0. And then the curing takes place rapidly. You need to irradiate until the adhesive is fully cured, and then it actually is fully cured and can take its full go. Let's look at some examples where those properties are put to use. One example would be fastening elements. Here on a BMW i3, where these onserts, as they are called, used to put bolts, where bolts are bonded onto this carbon fiber chassis. Another example would be sealing in electronics, especially when the geometry is complex like this, where a normal seal is not very easy to do. So the adhesive is applied, and in this case, cured. And then you have a kind of a sealing ring bonded to the bottom part of this housing, and you can use it just like a normal sealing here. And a very good example to show for these acrylates are also switches, relays, and connectors. A lot of them are being produced, so short cycle times are important. And the good sealing and good bonding properties to different different materials, become very handy for those kind of applications. Okay. Those were the acrylates. I'm going to switch to the light curing epoxies now. Again, some basic properties and how they behave. As you can see here, of course, they're light and UV curing. They're curing to initial strength possible in a few seconds. Now that's quite a bit different wording than we had with the acrylates. They are finished after irradiating. Those adhesives build up initial strength when you're finished with irradiating. So when we look down here on the reactions schematic down here, you can see that the time axis changed. Here it's second to minutes, and this is hours. And we're still looking to achieve 100% of curing degree. Now, at the time 0, we do switch on the lamp, and then there's a rapid increase in curing degree, and we build up initial strength, but the adhesive is not fully cured at that point. But, and that's the big difference to the acrylates, the reaction is going to go on by itself without any further irradiation. So over the course of the next maximum of 24 hours, the adhesive is going to fully cure without further irradiation. And of course, talking about some physical properties, they are a lot harder and stiffer, less flexible than the acrylates. So typically more on the lower end here, let's say single-digit percentages of elongation and tear. Their color changes from transparent to yellowish transparent. And there are, of course, some limits, pretty much the same as with the acrylates. Layer thickness must not exceed 5 millimeters. And there's, again, no curing in shadowed areas. You do need to irradiate the whole volume of the adhesive. But the fact that the reaction continues opens up a very elegant method and a very elegant option, and that is you can join non-transparent components through the process of pre-activation. And I'd like to show that to you now. This is the process we already talked about, classic light curing, direct light curing, dispensing, joining, curing. We talked about that. And now it's pre-activation. How does that work? So the goal is here to bond two non-transparent, two opaque components. So we'll start off with dispensing the adhesive on one of the components. But now we're going to irradiate to activate the adhesive. So now the process of polymerization has started. The adhesive is going to fully cure over time. And now we have the chance to join those two components that are non-transparent, and the curing is going to happen without any further irradiation. And that's a very neat thing, because we can now join two non-transparent components with all the advantages that light curing gives us. And let's see that process in action. So this is one of the applications here. We're in the interior of a car, more specifically in the air conditioning system, and the bonding task is to join this coil on top of the green printed circuit board, the PCB. So how does that work? The adhesive is being dispensed on the PCB, then it's being irradiated. Now the reaction starts. We can join the coil on top of that. But if you look closely, you can see that there is again some light shining on that. And why is that? The customer here does a very neat process. He or she is irradiating the components, and of course the adhesive under the coil is not being hit by the light, but the adhesive does squish out a little on the sides, and this fillet, as it's called, is being irradiated. That's going to build up initial strength pretty fast, and that's going to hold the coil into place so you can move the whole thing. The production can go on without any further waiting time, and the adhesive below the coil is going to cure by itself over the next hours. So very fast process here to join those two non-transparent components. And other application examples for this type of adhesive, as it's very robust, especially towards media, is chip encapsulation, where you protect a chip with adhesives. And for example, switch relays that are in the automotive world, maybe in the motor compartment, where the environment is very harsh, and therefore the epoxies are very well suited because they can sustain, they can survive even harsher environments than the acrylics. Very well, those are two types of light curing adhesive. So I'd like to summarize those two parts. So light curing adhesives do exhibit their strength if you need short cycle times, if you want to use the advantage of on-demand curing, if you're using temperature-sensitive components, there's no heat needed, and when the connection needs to be transparent. And Michael talked about the LED lamps and showed that there's a lot of experience and a long history for it. They are a stable intensity over a long lifetime, especially in comparison to the discharge lamps. We have very different lamp head designs for various applications, and those integrate very easily into a fully automated process. So thank you very much for your attention about the light curing adhesives and lamps. And now Philip is going to continue with how to analyze those adhesives. Thank you.